Welcome back to the course on physics of nanomaterials. In this week, we are talking about the area of nanomagnetism. In the previous two lectures, we have seen that we expect property modulation and changes in magnetic systems as their sizes and dimensions are reduced and taken to a regime where you can call them as nano systems. So, in today's lecture, let us talk about the dynamics of these nanomagnets, if we may call them as nanomagnets. So, you will see the mesoscopic magnetism and nanomagnets. What are the challenges in magnetic storage that needs to be addressed as we talk about miniaturization? One of the earliest system which was introduced by IBM, that is iron platinum, will be taken as an example today, and you will find that such systems, although very simple, needs to be very carefully synthesized using protocols which are non-trivial. But once you have synthesized them, you can make very interesting use of these nanoparticles. We will also talk to you about some of the other characterization techniques. These techniques were not discussed in the previous lecture, and we will see the theoretical model, the Stoner-Wohlfarth model, which explains the single domain nanomagnets. So, how we need to move from conventional models to modified models to explain the observations of these nanomagnets. So, if you talk about the mesoscopic magnetism, so we are talking about the magnetic behavior in systems which are in the mesoscopic scale, which lie between the microscopic, that is the atomic range, and macroscopic bulk scales. So, typically we are talking about systems in the range of, let us say, 1 to 1000 nanometers or so, but we will focus in the region of 1 to 100 nanometers. If you talk about this regime, then you will find that both classical and quantum mechanical explanations would have to be used to explain the magnetic properties. And once we have understood the origin of magnetism in such systems, then you can use them to various applications. Let us say we talk about the magnetic storage and bit miniaturization. Let us say if you want to have very high storage per square inch, now you can see you are carrying huge amount of data in your mobile phones without increasing the size of the mobile phones. So, mobile phones are actually becoming smaller while their speed as well as storage capacities are increasing. So, the size of the screen may be increasing, but the associated electronics is not increasing. That is why you do not see very thick mobiles. You can have large screen area, but the thickness of the mobiles are not increasing corresponding to the increase in the screen size. But your storage capacity is increasing. You can talk about 256 GB, 512 GB, and it is a huge amount of data. So, if you then for example want to store let us say 10 gigabytes per square inch, then simple mathematics will tell you then each bit will have to be approximately 1 micrometer wide and 70 nanometer long. In a magnetic film, which is approximately 30 nanometer thick, because you are talking about these particles behaving like 1 bit. So, 1 bit you can have of this size, and during the synthesis protocols you have already seen that making such kind of particles are very easy now. Hence, you can also make nanostructures using techniques like lithography, which have such kind of dimensions. So, you can easily get very high storage capacities. Now, traditionally the magnetic storage devices like the hard drives, they use cobalt chromium alloys. However, here there is significant challenge which is faced when you reduce the bit size to 10 nanometers or below. So, let us say one particle storing 1 bit, then if you have this particle which is less than 10 nanometers, then there is huge size induced property modulations, where random thermal vibrations would do what we have seen in the previous lecture. Because these particles are very near to the surface, and then because slight change in temperature can induce the magnetization vector to flip, and hence you will lose the data, and this is something which you cannot afford in today's world. So, to counter this, there was and there is continuing research activities to utilize nano size grains which actually can give you the capacity of higher saturation magnetization and also stronger magnetic interactions between the grains, because you are talking about elongated grain structure, and if you want to flip one bit with just by varying temperature, it is not easy, because the whole system is going to oppose it, and because it is going to oppose it, this change will not be energetically favorable. So, they are able to resist temperature induced variations. So, they become resilient to thermal agitations. One of the first materials which were used and proposed are based on systems like iron platinum. This has exceptionally high magnetization. Let us see how do we synthesize these iron platinum nanoparticles. It is basically a process which involves nucleation, then growth of iron, and finally you have atomic diffusion. The whole process involves the heating of the solution containing platinum acetonate and iron carbonyl along with a reducing agent. Now, oleic acid is introduced as a surfactant. As we discussed, surfactant is a system which has two ends, one is hydrophilic, other is hydrophobic. This prevents the aggregation of nanoparticles by coating their surfaces. So, once you synthesize these particles, they are spread onto a substrate and the solvents are allowed to evaporate, leaving a uniformly coated layer with iron platinum particles. This resulting films are then baked at temperatures say around 560 degree C. Now, this process allows stability in these structure, the ordered arrangement is induced and then confirmed, and subsequently they can be used for high density data storage applications. But how do we know that you are forming iron platinum? But how do you know that the system has actually formed? So, you have to carry out the characterization measurements. So, you start with let us say X-ray diffraction and you can confirm that there is a formation of iron platinum system after the calcination. Then you carry out the SEM or TEM measurements to determine the particle size and confirm the orderness in the formed system. We have to determine the magnetic properties and you can carry out the squid measurements and you get the MH curves. And you can also carry out as to what should be the mole ratio of the precursors at which you will get the maximum HC. So, you can confirm these things that the system is in the desired FCC phase. This phase has low magnetic anisotropy. Once you then calcine the systems, you can find that you are stabilizing a face centered tetragonal structure, which is responsible for the emergence of hard magnetic properties. The TM measurements will confirm the typical size of particles you are forming which still show magnetic response. And at this size, what can happen? That you can potentially achieve a storage capacity of 150 gigabytes per square inch, which is approximately 10 times greater than that of the conventional magnetic storage technologies. And their magnetic vectors align in an ordered single domain configuration under a DC magnetic field. So, now this eliminates the complications associated with multiple magnetic domains and domain wall formation, which otherwise lead to random orientation of magnetization in larger particles, and you also have loss of the magnetic storage capacities because of material degradation over multiple times of writing and rewriting on a larger size particles. This whole phenomena was actually explained by Stoner and Wolfart, which was published in 1948 and is named behind the two scientists which worked on this principle. They said that contrary to the conventional belief that system can be in two states, that is either in up state or down state. When you go to smaller sized, then on application of field only one of the directions become favorable and it dominates over the other. So, based on this concept of elongated grain and their response on the external magnetic field, Stoner-Wolfart gave the theory for understanding and explaining the magnetization of ferromagnetic systems. And if you look into this system, this primarily takes the assumption that you are considering single domain, that is there are no domain walls. The magnetization vector rotates coherently, there is no internal spin disorder, and particles have uniaxial anisotropy, that is one easy axis of magnetization. It also considered that the particles are non-interacting. So, you do not have any dipolar or exchange coupling in such systems, and external field is applied at an arbitrary angle theta to the easy axis. In this case, the total energy per unit volume can be written as E phi given by this equation, where Ku is the uniaxial anisotropy constant, phi is the angle between the magnetization vector and easy axis, theta is the angle between external field and easy axis, mu 0 is the permeability in vacuum, Ms is the saturation magnetization, and H is the magnitude of external magnetic field. So, you could actually write the total energy which would be there. What will happen? In the absence of magnetic field, the ellipsoidal magnetic particles have only two energetically stable orientation, either aligned up or down along the long axis of the particles. Now, this becomes very interesting in terms of elongated grains. Here, the energy landscape associated with these two orientations forms a symmetric double potential, where each well represents a stable magnetization state. Because of this, what happens? The energy barrier between these walls and which actually give you two well like structures determine the stability of the magnetization. Suppose one potential well is much smaller than the other. So, then what will happen? The other will become preferable, but we are considering initially this is the two orientations in a symmetric potential well. This is the classical picture, but when you talk about the quantum and confinement, you find that this variation gets modified and one of the directions become more preferable. This is clearly shown in this figure. So, if you plot energy versus magnetization direction, you will see that classically two states are possible, either the up spin or the down spin. But the moment you start talking about the quantum kind of structures, then one of these states become more preferable than the other. So, the other also starts flipping in the more preferred direction, and the particle may flip its orientation due to the thermal activation given by the Arrhenius process, which is given by a probability P proportional to exponential minus E by k beta t. The magnetic particles can also flip their magnetization via the quantum mechanical tunneling process, especially when you have k beta t much smaller, that means you are talking at very low temperatures. So, now what can happen, that when you go to very small size particles, one of the states are preferred than the other. So, this was the concept which was proposed by Stoner and Boltzmann, but because it has some limitations, that it overestimates the role of flipping, that it can only take one path to flip the direction. This is oversimplification. It also says that you will have very high coercivity. This also sometimes does not relate well with the experimental results. So, modification in these models were done, and as you make new systems, you get new observations, and this basic model needs even more refinement to explain the experimental results. But the fundamental understanding remains the same. Conventionally, we have always been talking about that in classical systems, two wells are equally probable, that system can stabilize in any one of them, but in the quantum picture, in magnetic systems which when taken to nano size, one of these states become more preferable over the other. And the probability of reorientation is also given using a simple Arrhenius process. So, when you apply the magnetic field, this reduces the barrier height, making one of the magnetization direction unstable at the coercive field. And therefore, the SW model could explain the magnetic behaviors in small particles. But as I said, it overestimates coercivity, because it assumes that it is always coherent rotation and ignores other reorientation mechanisms which are observed and seen in such systems routinely. In addition, the model presumes that the magnetic energy is a function of collective orientation of atomic spins and the external field, hence depends on the particle volume, and therefore, this assumption also leads to deviation from the experimental data, because magnetic energy is not always a collective orientation. You can have as a convoluted picture, but it is just not always as one simple mechanism which is there leading to the orientation of atomic spins. So, it is much more complicated, and therefore, the model sometimes deviates and is unable to explain the observed data. So, you can always refine these models based on the experimental results which you observe. So, for example, if you take a system, let us say, which are very small systems, here the surface atoms would dominate than the bulk. Hence, the magnetic behavior would be influenced by the surface atoms, which will behave differently than the atoms in the larger grains. So, the surface area becomes very critical than the volume which was being considered in the case of modeling of the SW model. So, one has to very carefully understand why such changes or deviation in models were being observed, and which parameters one has to look into to explain the observations which are there in systems of different confinement, and shape and size would also lead to various kind of complicated parameters. For example, magnetic structures with quantum well type morphologies or quantum wire type or quantum dot like, they are going to have different kind of contributions coming in from surface and the volume. Hence, the impact on the magnetizations would also be very complicated. Hence, you may find that the SW model may not capture the more complex dynamical behavior of very small magnetic systems. For every system you may have to modify these models which have been built upon the basic concept which was proposed by Stoner and Foltwarth, but overall this model gave the first theoretical model which can explain or could explain the magnetization at nanoscale. So, these are some of the other references which you can go through to understand even more details about the topics that were covered in this lecture. We have seen now that you can have very high storage capacities because of the use of nano sized magnetic particles. You can make new magnetic nanoparticles which would give you the capacity to make new magnetic storage devices. The chemistry of such materials would have to be carefully tuned so that you get the desired crystal structure, the phase, the particle size, the shape, the magnetization, so that the magnetic storage which you can get is maximized. We have also given you the basic fundamental model which was proposed by Stoner and Foltwarth to describe the dynamics of nanomagnets. With this, we finish the third lecture of this week, and I thank you for attending the same.